Good. So far we've talked about breadth first search and we talked about shortest path algorithms. And there's another sort of classic algorithm that you should know about called depth first search. Okay, so how does DFS work? The basic idea of DFS is much simpler than BFS. Remember that we start with a source vertex, right? So S is a source vertex. And so DFS actually does something. I'm just going to write this little snippet here. It just says for every vertex U in the neighborhood of S, I'm just going to put a plus over there. So this is the out neighborhood, because often DFS is used on directed. I mean, it's used both for directed and undirected. But, so if it's directed, you would do the out neighborhood, or you just do the normal neighborhood. For every U that has not been visited, we're just going to say visited of U is true, and then do a recursive call. And that's pretty much it. I mean, of course, there's more. I have to add some extra things that we keep track of, but the basic logic, this is it. So you can think of, remember, BFS uses a queue. Now DFS is doing recursion. And what is the data structure that captures recursion? It's a stack, right? And so DFS effectively, or I'll say implicitly, you can do it implicitly or explicitly, uses a stack. Now, if you remember from the things that we did in test 2, as well as the n queens, you have an implicit, you remember that recursion can be converted to a stack. And so I'm going to give you a description that is recursive, kind of like this. But you could convert that to a stack using the kinds of ideas we used. And that is typically how DFS is implemented. It's implemented using a stack. But it's easier to sort of conceptualize the algorithm when you think of it using recursion. Okay, so now remember that, so just to recall, BFS had these arrays, right? It had the predecessor and it had visited. And what BFS was doing was really, it could compute shortest path distances, right? Shortest path distances. DFS, on the other hand, so it's also going to have a predecessor array. It's also going to have a visited array, just like BFS, right? So this is going to give you the DFS forest. And this is the same, as the BFS visited array, right? Every time you touch a vertex, you set visited to be true. But the main new thing that DFS maintains is that actually maintains two arrays. So all of these are going to be arrays. All of these are arrays indexed, on the vertices, which I'm numbering from 1 to n. There's going to be a notion of time. So think of there's a clock ticking. And each time DFS does an operation, the clock moves by 1. So there is this global clock that's going to be there. And we're going to maintain what are called discovery times and finish times. So these are arrays of discovery and finish times. So this I'll explain, and this notion of time is kind of what makes DFS special. So BFS effectively computes shortest path distances. DFS is also going to construct a DFS tree or forest, but it is not going to have shortest paths. Instead, we're going to maintain something called a discovery time and a finish time. So let me explain a little bit about how DFS works. So I'm going to give an implementation of DFS. The implementation is recursive. Now, what's important to note in this is that there's going to be these are global variables. Okay, I'm going to give some global variables. And the global variables are time, which is just going to be it's just like, think of it as an int or an unsigned int, which is initially going to be 0. And then we have, of course, the predecessor, visited, discovery time, and the finish time. So these are global variables in the recursion. Again, the implementation is usually done using a stack. So how does DFS of S work? So the first thing that you do is, I'm just going to set visited of S is equal to true. Again, you don't necessarily have to do this. You'll see that it's also set as true somewhere else, but I'm just going to put this in for convenience. Then I'm going to say this is the time at which I discovered. So the time is this global variable, and then the time is going to increment. So the clock has ticked. Then you say for all vertices in the out neighborhood, if it's an undirected graph, then the out neighborhood is the same as the neighborhood, so there's nothing to be done. I'm going to say if visited of U is false, if it's false, then I'm going to set, okay, so I'm going to do, first I set the predecessor. I say the predecessor of U is S. And then, you know, just to be safe, so this is going to be useful, is I'm just going to set the visited of U is going to be true. So I'm sort of setting it in both places. You don't need to do that, just to be safe. I just want to emphasize that, you know, whenever you call something, it's visited. And then we're just going to make a recursive call to DFS of U. Finally, we're going to say the finish time of S is equal to the time, and then the clock ticks. Okay, so this is DFS of S. Okay, DFS of S. And DFS on the entire graph would simply be, you know, initialize all these arrays. So you initialize all the arrays. You set time is equal to 0. And then we'll say for all vertices S, if visited of S is false, then we're just going to run DFS on S. Okay, so this is the basic code. Okay, this is the basic code of DFS. Okay, any questions? I'll work out a little example, and you kind of see, we'll see how this thing goes. But any questions about what is being said here?
So you're picking a random starting point until there's no random starting points left?
You mean in the DFS on the graph?
Right.
Exactly. So someone said if you take the BFS code and replace the queue with the stack, it's basically the same thing. But you have to, that is exactly what is happening there. You are just replacing the queue with a stack, but then you have to be a little careful about these notions of discovery times and finish times, and we'll talk about these. Like this is the power of DFS. You can use these discovery and finish times to do many fairly surprising things. And I'll say that the logic for BFS and DFS in terms of running time is exactly the same. So the running time of depth first search on the entire graph is linear, right? So it's a linear time procedure. Now, so let me ask a question. Suppose the graph is undirected, okay? There's going to be a DFS forest. Can you tell me what are the individual trees? What do those trees give you? They give you something that you also get through BFS. So what do they give you? Question clear? What are the trees of the DFS forest when the graph is undirected? Any thoughts?
Wouldn't it be like not the shortest path, but it would be some like the depth first?
So ignore the path. So each tree is like some set of vertices, right? What are those sets? So suppose you have a graph. Okay, let's talk about BFS. Suppose you have a graph and you run BFS. What are each of those trees? What is each? So you get these, each tree is a set of vertices. What is that set called? Okay, let me try to ask the question differently. Suppose here's your graph, right? There are a bunch of edges in here, a bunch of edges in here, and a bunch of edges in here. How many trees is the DFS forest going to have?
3.
Why?
Once it finishes with one DFS, it'll look for another vertex in the graph that's not connected to the first tree.
Exactly, right? So because if you start DFS in here, you're eventually going to visit everything. Right? You're going to visit everything eventually. And when you visit everything, you will get, so the trees are connected components. But I want to emphasize the trees are not the same. You can get very different looking trees. The trees are not going to be identical. And someone said, no, it's not going to produce the same predecessor array. So this is going to take an example to understand. So let's consider, I don't know, some graph like this. And maybe I'll do that. Okay. So let's give these names. So I'm going to call this vertex, call it 1, 2. Well, let me call it V1, V2, V3, V4, V5, V6. And you know what? I'm just going to make it interesting. I'm going to put an edge like that. Okay. All right. Now I'm going to change the numbers a bit. So there's V1, V2, V3, V4, V5, V6, right? And so let's just say that we call DFS on V1. Okay, so that's like your initial source. So I'm just drawing out the tree over here. Okay, so initially you're going to get V1. Now V1 is going to pick any one of its neighbors, right? It's going through its neighbors in some order. And so it doesn't have to be exactly in this order. So maybe V1 decides to go here first. Right? So what could happen is that V1 could call things on V. And so in this case, I should also say that the discovery time for V1 is going to be 0. Is this clear? The discovery of V1 is 0. So I want to make this a little interesting. So I'm going to have to think a little bit about how to do that. Yeah, let's do this. Okay, maybe I'll make a V7 over there. Okay, so let's say V1 decides to call V6. Does that mean DFS of V6 is called? So what's going to happen is that this vertex is going to gain a child, V6, right? Because start at V1, which is discovered. So I'm sorry, this is going to be visited. Then V6 is going to be visited. And what is the discovery time of V6? So what is the discovery time of V6? So let me show you that code again. Remember, the clock is ticking. Maybe I'll zoom out a bit so that you can see the entire page. Right? Okay, so what is, sorry, let's zoom it. There you go. So what is the discovery, sorry, what is the discovery time of V6? Remember, we initially called it on V1. The discovery time of V1 is 0. 1. Exactly. It's 1 because when you discovered V1, the clock ticked. Then you went in here. You made a recursive call. So you go back there. And then you set the discovery time. And the discovery time is 1. Okay? Now from V6, maybe we end up visiting V5. So V6 is going to get a child, V5. What is the discovery time of V5 going to be? What is the discovery time going to be? Yeah, any thoughts? It's going to be 2. And then from V5, you're going to call, and note that you're not doing what BFS does. BFS would put all of V1's neighbors into a queue and go through the queue order. Here, it's almost like going through a maze. You go from here, you visit that. You go ahead and visit the next one. You just keep visiting until you get stuck. So watch how it goes. So you visit this vertex. Then you go there. You say, okay, I'm going to now visit this vertex. Now the discovery of V3 is going to be 3 because the clock keeps ticking every time you visit something. Every time you set a discovery or a finish, note that no procedure has finished yet. So the recursion has not yet completed. Right? The recursion is not yet completed. So from V2, you're not going to visit, from V3, you might visit V2. So the discovery of V2, that's going to be 4. Then from V2, we visit V5. And so, I'm sorry, the discovery of V4 is going to be 5. And so V5 is going to have a child V3, which is going to have a child V2, which is going to have a child V4. Note that the path from V1 to V4 is that. Is that a shortest path? Is this the shortest path? No, it's not, right? Because the shortest path would go from V1 to V2 to V5. You go that way. This is not a shortest path. Now what's going to happen? Can someone say what's going to happen now? So V4, you're running DFS on V4. What is going to happen? What is going to happen?
No, we're going to fill in the end times, going back up the chain.
You're going to fill in the end times because now the procedure has ended, because V5 is going to go through all of its neighbors, but they're already visited. So it's going to finish. And so what you're going to do is you're going to set the finish time of V4 is going to be what? Exactly, the end times are coming. Finish times. What is the finish time of V4? Remember, every time something is discovered or something finishes, the clock ticks. right? It's going to be 6. So not 5, because once anything is discovered, the clock ticks. So you never have 2 times that are the same. So the finish time is going to become 6. So V4 finishes at 6. Now who gets called? Now what's going to happen? What is the next thing that's going to happen?
V2 would end.
V2 has to finish. Exactly. Why? Because V2's recursive procedure is still running. V2 called V4. V4 finished. So it goes to V2. V2, all of its neighbors are visited. So V2 is going to finish. So the finish time of V2 is going to be 7. Then the finish time of V3 is going to be 8. The finish time of V5 is going to be 9. Then what happens? Then what happens? So V5 just finished.
V6 has to visit his neighbor.
Exactly. V6 is going to visit all of its neighbors, which one of them is still not visited, which is V7. So it's actually going to visit V7. So what's going to happen now is a new vertex gets discovered, V7. So it's actually going to discover V7 and set that time to be 10. And who's the parent of V7? Who's the parent of V7?
V6.
6. So V7. Okay, so now that gets visited. And then V7 is going to immediately finish. So the discovery of V7 is going to be 11. Then V6 is going to finish. So you're going to finish V6, and that's going to be at 12. Finally, you finish V1.
Did you mean the finish of V7 is 11?
I'm sorry, you're absolutely right. The finish of V7 is going to be 11. Right? So does this sort of make sense? So this tree, it's actually something that you should be familiar with. What is this tree? What is this tree? What does this tree like tell you?
It's the call stack.
It's the call stack. It's the recursion tree. So this tree is simply the recursion tree of calls. Right? And the time is just the time that a procedure starts and the time that a procedure ends. That's it. Right? Does that make sense? Now you might think, why is this useful? Like, what is it that we're learning from this? And for that, I'm going to have to give you an example of an application of DFS, which is really neat. But I hope this makes sense. Did this running the algorithm make sense? Any questions? Okay, good. Okay, so now let's go ahead and let me tell you about a problem where DFS actually gives the ideal solution. It's actually something that you might be familiar with, which is code dependencies. Okay, so what do I mean by code dependencies? So let's say you have a file. There's some file foo.c or foo.cpp or whatever have you. Okay. Now, what you might decide to do is, you do some sort of hash include, and you decide to include a file qwe.c. Okay. And there's another file here, which is include foo.c, and let's call this bar.c. So this is going to be qwe.c. And suppose this doesn't include of bar.c. Do you see a problem?
Yes.
What is the problem?
The problem is that only it's trying to exist with the other bike bar.c can only exist by foo.c, but foo.c can only exist through qe.c. But one can't exist without the other. It's like a paradox.
So it's actually, as I think, as someone put on the chat, this is called a dependency loop. Meaning that if you want to compile foo.c, you have to include qwe.c. So you go to qwe.c and say, okay, I need to include this. This says include bar.c. This is okay, go to bar.c and include that. Then this says include foo.c. So you actually cannot compile this code. We cannot compile the code. And the way that you represent this is you can represent this. So you can represent as a directed graph. Okay, so how do you represent as a directed graph? You say, well, you can try to say who needs to be compiled first. So if you have this is include qwe.c, then you say, okay, I'm going to put an edge that goes like that. That directs this. This means to compile foo.c, you have to compile qwe.c first. Now this is include bar.c, so we'll put an edge from bar.c to here. Now from bar.c, you say include foo.c, so we put edge like that. So what you get is a directed cycle. A directed cycle means that is equivalent to saying the code cannot compile, and this is also called a dependency loop or cycle. So your compiler needs to figure this out before it can start compiling. Okay, so the way that this is represented is we're going to consider a graph G, V, comma, E. V, the vertices are going to be a collection of files of code, right? And UV is a directed edge, right? This means that U goes to V if V hash includes U, right? What this means is that U must be compiled before V. Okay, and a directed cycle, it's easiest to draw this is just saying that suppose you have V1, V2, V3, V4 up to Vk, such that there are edges that go from V1 to V4, so on and so forth, and there's this other edge. This is called a directed cycle. A proper, so a DAG, this is a very important term, is a directed acyclic graph, meaning it has no directed cycles. Now, I just want to emphasize that this is not a directed cycle. This is not a directed cycle, this over here, right? Because you can have, like, this might look like a cycle in the undirected sense, but in the directed sense, this is not a cycle, because you can go from this vertex to the next vertex, come down, but you cannot go back. right? Because you have to follow the arrows. So a DAG is a directed acyclic graph, okay? And a dependency graph should be a DAG. We cannot compile, indeed, actually, if G is a DAG, then we can compile. And actually, it's if and only if. It's actually if and only if. Meaning that if G is a DAG, we can compile. And if we can compile this code, it must be a DAG. Okay, does this make sense? The concept of a DAG, a directed acyclic graph. Any questions? Okay, so we can think of a problem, an algorithmic problem. The problem is, given the adjacency list of a directed graph, determine G, determine if G is a DAG. Right? I give you an adjacency list and I say, okay, is this a DAG or not? Can this code actually be compiled? Does that make sense? Right? So this is one question. The next question you might ask is, well, okay, suppose G is a DAG. Can we find an order of compilation? Okay, so I'm going to put this in quotes. What do I mean by an ordering? So let's just draw a DAG. Okay, so this is V1, V2, V3, V4, V5, V6, okay, and go ahead, I'm gonna is this a DAG?
No, it does loops.
What's the loop?
Well, I guess you can go from V. Oh. Yes.
Is this a DAG?
Right, it is.
It is a DAG. Right? What you'd like is an order to compile the code. So what would be an order in which you could compile this code?
I mean, first you'd probably want to do the ones with only edges pointing out.
So someone said random. I want to make sure. So how can you compile this in a random order? If this was actual code, so this is a dependency graph, right? Someone said you just do it randomly until you can try again. If you did that for a large enough piece of code, it would take an extremely long time. But I want you to just, can someone just tell me in order? Like, what is the first node that you would start with? What is the first thing that you would compile?
V5.
V5. Why?
Nothing's pointing at it.
Nothing's pointing at it, right? So you start with V5. Okay, then? Okay, then V2. Then you could do V1. Then you can do V6, then V4, and V3. Okay. Is there any other possible way of doing it? Is there anything else that I could do?
I mean, you could start at V5 and go to V3 first or something.
Can you? What's another ordering? There's another way in which I could do it. There is another one. No, I cannot do V2 first. I cannot do V2 first because I cannot compile V2 before I compile V5. Okay, so someone seems to have it. Someone says swap 1 and 6. Okay. What about this? V2, V5, V2, V6, V1, V4, V3. Both of these are valid. But what am I really doing? Can you tell me something about this ordering with respect to the edges of the graph? Is not BFS really. It's not BFS. If you think about this ordering, if you did BFS from V5, you would actually go to V3 first. But in all of these orderings, V3 is at the end. When you start at V5, if you did BFS, you would go to V2 and V3. But this isn't doing that. So don't think about depth first search or breadth first search. Just tell me, what is it about this ordering and the direction of the edges? There's some pattern here. Like this, these are okay. But this ordering, this is not okay. Why is it?
Because V2 does not point to V4.
No.
Also, V5 appears twice.
Okay, that is definitely a problem. But I wanted to do, which one is missing here? V1, right? V1, sorry, there. Yeah. So why is it that I can do these orders of compilation and not this? I hope the question makes sense. Yeah.
Why are we starting at V5 again?
Why are we starting at V5? So what is the rule, right? You want to compile code. And if you ever have an arrow into something, then you have to compile what's at the other end first. Does that make sense? So if you wanted to compile foo.c, you have to first compile qwe.c. That's what the arrow means. So you sort of follow the arrow backwards and you have to compile that thing first.
Oh, okay. Thank you.
And so over here, you start at V5 because V5 doesn't have anything pointing into it, so it can compile first. It's not as easy as DFS, like, okay, we'll come to DFS, but someone tell me, why is it that these are okay and this is not? There's a very clear reason why these orders are okay and this order is not. What is wrong with this order?
It's because V2's only has 2 arrows to V1 and V6 and not V4, so it can't traverse to V4.
No, that's not true. This is not a traversal either. So from V5, I did V2, and then I did V6 after that. So V5 cannot go to V6. V5 is actually going to V2 and V3, and V3 is at the end. Okay, so someone said only visit nodes whose dependents are compiled. Exactly. V4 cannot be visited before V1. Exactly. Like you cannot, well, visited is you cannot compile V4 before you compile V1. So this is wrong.
Wait, for V4, would V1 and V6 have to be compiled?
Exactly, right? Both of them have to be compiled first, right? Because if you hash include 2 files, then you have to compile both of them first.
Right.
So now tell me, what is it about these orderings that's correct and this ordering that's wrong? If you actually were to draw the arrows, you would know what's going on. So I'm going to draw it for you, okay? So let's draw the arrows on my own. V5 to V2. Okay, that's that. V5 to V3, okay. V2 to V1, V2 to V6. V1 goes to V4. V6 goes to V4, and V6 also goes to V3. Do you see a pattern here?
They're all compiling before any of the ones that they're pointing to.
Right, so what is it about the arrows that you see here in this ordering?
They all point the same way.
They all point in the same way, right? They're all pointing left to right, right? If you look at the second case, this is also going to do exactly the same thing. V5 is going to go to V2, V5 goes to V3, V2 goes to V6, V6 goes to V4, V2 goes to V1, V6 goes to V4. I think, is that it? I'm missing something. Yeah, V6 goes to V3. But in this ordering, you have V1 pointing to V4 in this direction. That's why it's wrong. So you see that in the first two orderings, the arrows always point from earlier in the ordering to later in the ordering. It's not a traversal, it's an ordering of the vertices. These are orderings. There's an ordering of the vertices. And this has a name. This is called a topological ordering of the vertices of a DAG. Okay. So what this is I'm going to call it a sorting, but really it's an ordering. It's an ordering of vertices so that edges always point from earlier vertices to later vertices. Does that make sense? It always goes from earlier to later. So is it only true you can access something once all of its dependencies are compiled? So you could have V5, V3, V2, V1. So in your example, in V5, in what's written in the chat, so you're saying V5, V3, V2. No, your problem in that case is that V3 also depends on V6, right? V3 depends on two things. It depends on V5. It also depends on V6. So you have to do both of them first before you can get to V3. And in your example, you're doing V3 before you did V6. And therefore, it's not a valid topological ordering. So a topological ordering of vertices is to order the vertices of a DAG so that this happens. Do you see that if a graph is not a DAG, you cannot topologically order? Because no matter how you put the vertices, if there's a directed cycle, something is going to go back. Okay? Is this clear, the notion of a topological ordering? Please ask questions, because this is one can get confused. It has nothing to do with BFS or DFS yet. This definition is not about, it's about ordering the vertices so that you go from earlier to later. Questions? Any questions about this? Okay, so I just do a quick poll. You know, A is I understand what's going on, and B is I'm confused. Okay. So for those of you who, I mean, I think most of you understand. For those of you who are confused, this is a good time to ask questions. All right, so it seems most of you are following. So maybe I don't understand the question on the chat. It says DFS, but if a node doesn't have its dependency compiled, it moves back to the queue. Are you suggesting an algorithm to do it? Then, you know, yes, you could try to come up with things like this, but good. Okay, so I'm going to come up. It turns out there's actually a much faster algorithm. What you're suggesting might actually take a long time. I think it can work, but then you have to sort of move things in the queue. It turns out there's actually a surprisingly elegant algorithm, but let me first write the problem. The problem is given a DAG G, output a topological ordering of the vertices of G. Okay, is this clear? So output a topological ordering of the vertices of G. And I just want to sort of emphasize that if G has a directed cycle, it does not have a topological ordering. Okay, now note that a topological ordering is not unique, and I just gave you an example where there are two distinct topological orderings. So we have two problems, right? And I've sort of stated them here. The first problem is given the adjacency list of a directed graph, determine if G is a DAG. The second problem is given a DAG, output a topological ordering of the vertices of G. Both of these are fundamental problems that come up in compilers. So when you write a compiler, or even if you do something like make, when you run make, it has to determine if these dependencies are all okay. And so when you set up dependencies, or like GCC, when you compile code, it will often tell you there's a dependency loop if there isn't. How does it figure out these things? Because what it has is really, it just has access to an adjacency list. It just knows which files include which other files. So that's like an adjacency list. How does it actually find these things? And so it turns out both problems can be solved in linear time, which is the most efficient, in linear time using a single depth-first search. So just like we could solve shortest paths in graphs using breadth-first search, we can solve this problem using depth-first search. All right? And so I'm going to first tell you the algorithm itself, and then we'll discuss a little bit about how it works. Any questions at this point? No, please feel free to ask. So there is actually a theorem which says, suppose G is a DAG, then the reverse order of finish times is a topological ordering. So THM means theorem, because this is like a mathematical statement. So it's simply saying that every time a DFS call finishes, push, let's say DFS V, push V onto a stack, and the stack has the topological ordering. Okay? So in linear time, what this says is, so I've told you how to solve the second problem, and I need to tell you the first problem. But I will talk about that. But is this clear? So it says the reverse ordering of finish times is a topological ordering. And so what you do is you just do depth first search every time a DFS call finishes. So to remind you of the depth first search code, here is the code for depth first search. So every time depth first search makes a call and it finishes, you could just push S onto a stack. So it's kind of the opposite of the call stack. So you push this onto a stack, and the ordering in the end is a valid topological ordering. That is the ordering on the stack. So it's not obvious to prove, and I'll discuss a little bit about that. But I hope the algorithm makes sense. Are there any questions about the algorithm itself? Okay, good. Now you might say, well, okay, that's fine, but how do you know if a graph is a DAG? How do you actually determine if a graph is a DAG? And so what you can do is, now this is, I'll have to give you another theorem and another concept. So let's run DFS on G and get the DFS forest. Okay, now I'm going to give a definition. I'm going to give the definition. And the definition is a back edge of the DFS forest. So what is a back edge? So UV is a back edge if U is a descendant of V. What this means is your DFS forest looks something like this, and a back edge is an edge that goes from a descendant to an ancestor. Okay? Is this clear? It goes, so if G is a DAG, if G is a DAG, can you have a back edge? If G is a DAG, can you have a back edge?
No, otherwise then it wouldn't be a DAG.
Exactly. You cannot have a DAG because that would give a cycle. So if G is a DAG, there are no back edges. If G is a DAG, there are no back edges. Now there is a theorem that states the converse. The converse is not as easy to prove, but it says if the DFS forest has no back edge, then G is a DAG. Okay, this is not obvious. It says that if the DFS forest has no back edge, then the graph is a DAG. This is the converse. This is the converse of this statement. So this is an easy statement to prove, that if G is a DAG, there are no back edges. That should be fairly easy to see, because every time you have a back edge, you have a cycle. And if it's a DAG, then it has no cycles. But this theorem is the converse. It says that if there are no back edges, then the graph is a DAG. Okay? Note that these two statements are different. I just want to make sure that everybody is following.
But you can convert one into the other.
What do you mean?
Well, like they're equivalent but different.
Yeah, but yes, you have to prove that they're equivalent.
But in this case, it could be done.
In this case, it can be done, yes.
Okay, cool.
In this case, it can be done. So I'm just going to ask a poll again. Does everyone see that these two statements, the first statement and the second statement, these are different statements? Okay, so A is, just going to relaunch the poll. A is, I understand that these are different statements. B is, I'm confused. These two statements are different statements. A is, yes, I see that they're different. If G is a DAG, there are no back edges. If there are no back edges, G is a DAG. These are two different statements. They are different but logically equivalent. No, they are not logically equivalent. They are not logically equivalent. These are two different statements. The first one says, if G is a DAG, then you have no back edges. The second one says, if there are no back edges, then G is a DAG. And it could be the case that, so it turns out in this case they're equivalent. These are not equivalent statements. The implications are in opposite directions. Okay? P implies not Q is not the same as not Q implies P. That's exactly right. P implies Q is the same as not Q implies not P. Okay? They're different. Right? They're different. Right? So this is important, right? These are distinct. So if right, this is just to give you an example in this context. I'd like to say something over here. So I'd say that, for example, I could say something like, if the graph has one edge, then the graph is a DAG. Right? If the graph has one edge, the graph is a DAG. Because if you have only one edge in the graph, so if the graph has one edge, the graph is a DAG. But the converse is obviously not true. If the graph is a DAG, that doesn't mean it has one edge. Right? So these implications, they're different. Okay. So, any questions?
So just jumping the gun here.
Yeah.
It is going to end up being the case, though, that having no back edges and being a DAG is like synonymous. That those things are actually the same thing.
Yes. The correct logical term you would use is equivalent.
Equivalent. Yeah. Sorry. Thank you.
Right? They're equivalent. These statements are equivalent, but you have to prove that they're equivalent. And so the power of DFS is that it gives you a linear time way of checking this. So what is the algorithm for determining if G is a DAG? So what you do is you run DFS of G and get the forest. Now the forest is stored in the predecessor array. And for every edge UV, check if it is a back edge. How do you check if an edge is a back edge? How do you check this? How do you check? And for this, you're going to have to go, to some extent, all the way back to the original pictures. How do you check if an edge is a back edge? Okay, how do you check if edge is a back edge? Keep track of visited. Good. So you can do it during the algorithm by keeping track of visited. But the way I've described the algorithm here is I just got the forest. I don't want to make any changes in DFS. So I got the forest. Can I just look at the forest and determine if something is a back edge? Okay, so
You remove that information because you never visit the same node twice.
right. So how do I know? So, but I claim that if you look at the finish times and discovery times, you can determine if something is a back edge. Okay, so let me ask you a question. Suppose V is an ancestor of U. Okay, so you have some okay, so this is U, that's V. Ask a question now, is the discovery time of V greater than the discovery time of U? So A is yes, B is no, and C is the question is confusing. Okay, so here's a question. I want you to think about it. Think about discovery times, and I'll just launch the poll. Yeah. So if V is an ancestor of U in the DFS forest, remember, okay, so go ahead and answer and then I'll clarify it. I'll clarify on that. Someone asks, would you have to check whether or not V is an ancestor of U? No, yes, I'm just saying that suppose V is an ancestor of U. Is this true? Is the discovery time greater than the finish time? Is the discovery time greater than the finish time? No, this is not assumed here, someone said. So I'm just saying that suppose V is an ancestor of U in the DFS forest, right? So you ran DFS and you got something that looks like this. So in the DFS forest, V is an ancestor of U. Is the discovery time of V greater than the discovery time of U? So the majority of you got it right. The answer is no, but why? Why?
Because V is discovered first before U.
And how do you know that?
Because it's because it's a directed graph and we're starting off with V, or
but
at least
you don't know. I mean, maybe there's something else in the forest. The forest looks like this,
Oh,
right? It could be anything. There, the forest looks at, I just said that V is an ancestor of U. So you're not starting with V. You're starting with something else.
Oh, okay. Well, in that case, if we
Let's
start
go back
at
to
any,
Hmm?
if we start at any point, V is most likely to be discovered earlier through the implementation of DFS before you.
Why? Okay, so remember, okay,
Not
I
sure.
said, what is this tree? What is this tree? It has a name, right? We discovered, we discussed this. What is this?
Recursive.
It's the recursion stack.
Recursion stack, yeah.
Or the recursion tree. This is the recursion tree. Now, what is it? You know that at some point there is a call to DFS of V, and at some point there is a call to DFS of V. Right? And the tree is the recursion tree. So what does that tell you? If you look at this tree, and if I said DFS, which one was called first? Was DFS of V called first or DFS of U called first? DFS of V, exactly. As someone said, it's because V is in the stack earlier than U. Right? In some sense, this is the recursion tree, which means that DFS of V was called before DFS of V. This is tracking, like, okay, ignore this edge here. This was sort of confusing. This is tracking the order in which things were called, right? So DFS of S was called first. Now, amongst these two, you're not necessarily sure which was called first, but DFS of V was called before DFS of its child, which is called before DFS of its child, so on and so forth. This is because the tree is tracking the order of the recursion, right? So actually, it has to be the case that discovery of V is less than the discovery of U. Does that make sense? This
Yes.
tracking the recursion.
Because tracking the recursion, V is most likely to be called before you.
Not before you, after you.
After you.
Right? Because whoever is higher up in the recursion tree was called earlier. Which of these finished first?
U.
Why? Someone said U. Why is U finished first?
Because it's like a stack. And it goes up the other way when you do the finishes, right? So the U is the last on the line.
Okay, what if there's more?
Then the ones after you would discover last and finish first. And then U would finish after them, and then V would finish after that.
Good. You have the idea. There's a more succinct answer, right? This is the recursion tree. What do you know about recursive calls?
They're recursive.
Well, yes, of course they're recursive. But if V makes a recursive call to U, then the recursive calls have to finish first before U can finish, V can finish, right? I mean, the whole point of recursion is when a parent makes a call to a child, the child has to finish first, and only then can the parent finish. That's just basic recursion, right? So this means that the finish of U, is going to be less than the finish time of V. Right, so just to draw this out, sort of imagine this is like the arrow of time, right? This is time. Which one do we see first? We first discover V. So I'm going to write this out as discover V, and I'm going to put this with a bracket. Then at some point, you discover U. Then as time goes along, you finish U, and finally, then you finish V. This happens, this is equivalent to V is an ancestor of U. So just by looking at the discovery and finish times, you can determine if V is an ancestor of U. And so this check over here, to check if something is a back edge, this can be done in constant time. This can be done in constant time. Okay, does this make sense?
Yes. As you recursively call through the tree, it will first try discovering through all things above the branch, but then as it recurses back, all things that are earlier up the branch will have a higher finish time.
Well, finished earlier. So
yeah.
And the way to think about this is because the tree, the DFS tree, is the recursion tree. And so things that are lower in the tree are going to be discovered later and finish earlier. Okay? And so you can determine if an edge is a back edge in O of one time. In O of one time. This picture of time over here is exactly what happens when the recursion occurs. Okay? All right, so I'm just going to pause for a couple of minutes. I just want to get a drink of water, and when I come back, I'll wrap up the discussion. All right. Any questions about this? I should have probably kept this over here. Any questions about this? So I want to emphasize again that we have, just to sort of recap what we did today. We talked about depth first search. We talked about depth first search. And the idea in depth first search is quite simple. It's just recursion, right? It's like some people think of it as traversing a maze. That, when you start at a vertex, you start at a vertex, and you go to the next vertex. You just keep traversing vertices until at some point you get stuck. At some point you might get stuck because all the vertices, the neighbors are visited, and then you just kind of go back and then visit other things, so on and so forth. The key data structures used in DFS are this notion of discovery and finish times. And so we discussed how DFS works in terms of its code. So there's DFS, there's a time that is ticking, and then one visits all the neighbors, and then sort of does things recursively. And in DFS on the whole graph, you basically just, you do the usual, just like BFS. For all the vertices S and V, if visited is false, then you call DFS on S. And you can see that, and just as the same logic as BFS running time, the running time of DFS is theta m plus n. Someone had a question about BFS runtime. This is a good time to ask that question.
So looking back at my notes when we talked about the BFS, basically the pseudocode for that boils down to hang on 1 second. Okay, basically it's a for loop inside of a while loop. For every neighbor of you do stuff, and then you do that as long as the queue is non-empty.
Correct.
Now, later on, we realized that BFS on a point S is theta m, where m is the number of edges.
Correct.
I'm assuming that's assuming that like m is greater than n. That's
not really. That doesn't even assume that. It actually is theta of m for a single, even if, okay, so if you look at DFS on S or BFS on S, that runs in theta of m.
Okay.
Because, okay, so the way that, it can be confusing when you have like, when you have a for loop nested inside a while loop.
Yeah.
The natural instinct is to like multiply the times. You say, oh, it's a nested loop, just multiply the times. But you have to be more careful here. You don't multiply the times because you realize you can do better by tracking when an adjacency list is actually traversed. And what you yes.
I was thinking, because when I looked at it, I kind of felt like it was actually worse than O of M, because the for loop basically says for every neighbor of this point, and the while loop basically says for every point, which implies that you're counting each edge multiple times, because the for loop doesn't know if you've taken the vertex at the end of this edge until you've checked it. And even though you're not running code because you've got an if statement there, it's still in the for loop. So it's like it should be greater than n, right?
No. So the way to think about it is, okay, so I might as well just pull out my BFS, whatever my notes on BFS, and just talk through that, because that is relevant to the DFS running time. So hang on, let me bring that up. Just give me a moment to bring out my code for BFS of S. Okay, so this is, I think, what you're talking about
That's it.
While loop and the for loop, right? Now, okay, the first thing you need to observe is okay, so you have to sort of, let's try to think about the logic differently. Every vertex is dequeued at most once, right? That should be clear. Right? It never goes back into the queue, because once a vertex is in the queue, it's visited. And once a vertex is visited, it's never going to go back into the queue. Do you see that?
Yeah, so the while loop is O of n.
Yeah, but now, yes, the while loop is O of n, but let's be a little careful. For every time something is dequeued, you visit its adjacency list. That's what the for loop does. The for loop traverses the adjacency of U.
Oh, wait, so is m the number of edges in the graph, or is it the number of items in all of the lists?
Isn't that the same thing?
Well, no, because there's repeats, right? Like
Is at most twice.
Oh, which is still a multiple of
2 times m. So O of 2 times m is O of m.
Okay. So then I would think it would be n times m then.
No, because for each run of this outer loop, this
you're right.
run m times. It only runs for the degree of that.
Okay. So that only runs m times. And I guess I ran into troubles on some of the practice problems, because basically you had to use BFS, but then like change it a little bit.
Yeah.
And I was wondering if you can always assume that the while loop and the for loop is basically m, and then let's say you have another for loop inside, then you could say it's just m times whatever you have on the inside of there.
You have to be a little careful with that. You can make such arguments. I didn't do these arguments in detail. You have to be a little more careful. It's not as easy as the old runtime arguments where you simply multiplied things.
Okay, so we just have to do our best.
You do your best. I mean, the thing is, usually you need to make a more careful argument. And overall, one way to think about it is if you use BFS as a black box, then things are easier.
Oh, okay.
If you just call BFS, like take your graph, make a change, call BFS.
Can we say like run BFS, except every time you do this, also do that?
You could do that. Then you have to be a little careful about the running time then.
Okay.
Like you're right. You can say things like that. You have to be a little careful about running time. And that's why I said the graph problems are a lot harder.
Yeah, because most of the solutions that at least I came up with seem to involve writing out the entire code to BFS and then adding stuff into it, which is not the same as just saying run BFS and then do something after that. Precisely.
But if you make changes that are only like O of 1 changes, then it still runs an O of n plus n.
Okay, cool.
If any change you make only changes whatever is happening in all of this by a constant, then you don't incur any other loss. Does that make sense?
Yeah, that makes sense.
Yeah, but I agree. Those questions are a lot harder, and they are much more challenging. And the running time analysis is also a lot harder to determine. Okay, so I think we're out of time, but I'll just quickly summarize. So we have depth first search. The important things to know about depth first search are really this concept of a DAG, which is sort of where depth first search is used quite heavily. So I'm just going to bring this stuff back up. There's the notion of a DAG, there's the notion of a topological ordering, and you can then use DFS to compute topological orderings and to determine if a graph is a DAG. And someone said, did you explain how to check if an edge is a back edge? Yes. Okay. So sorry, that may have gone through a little quickly. How do you determine if something is a back edge? You just check these conditions. So you take an edge UV, you check if the discovery of V is less than the discovery of U, and the finish of U is less than the finish of V, then V is an ancestor of U. So you just check these conditions for every edge. And if any time U is an ancestor, V is an ancestor of U, then it's a back edge. So if this condition holds for any edge UV, this is a back edge, and then you can say this is not a DAG, and you're done. Okay? All right, so I'm going to end now. I'll take any questions that you may have. And I will, the last lecture, as I said, is just open to any questions that you may have.